Hello, hello, hello. Something is happening here. Yep, the webinar is going to be started very soon. So I still see people are coming. So let's give it a few last seconds and then we will start the webinar. Okay, I hope everything is working. I hope everything is working well. So it definitely starts in a few seconds. Okay, so on my clock it's 2:01, so it's definitely, I guess it's time. It's time to start. So yep, hello everyone. This is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we will again talk about CFD, FEA, and FSI, and perhaps optimization on Francis Turbine, which is a workflow. We would like to show you how we do it, and maybe you will like it and think about it to go with us. So yep, let's start with a couple of cleanup here. So this is me, Luboš Pirkl. I will guide you through the webinar today. My colleague Radek Máca is a fantastic engineer and also he's fantastic father, and that's why he's today not going to be with us. So he had to do some parental stuff. So this will be just me today, but I believe that I will show you quite a lot of tips and tricks, and I believe that it will be another point of view how to do simulations, and it will be kind of CFD coaching, and maybe it will help you to think about simulations from a different perspective. So I believe there will be enough added value for you. So I'll do my best. So it's webinar 87. And it's going to be about Francis Turbine and about CFD simulations in general. I would like to ask you to ask your questions. So please ask your questions, use your time to the fullest. Ask about anything about simulations, specifically about Francis Turbine or anything else more in general. At the end of the webinar, I will pick the best questions that fit the topic, and I will answer them directly right in the webinar. The rest will be answered later via email, but you can be sure that all the questions will be answered. That's our condition. We always do that. So ask your questions and use your chance to talk with us. The webinar is being recorded. I hope it's being recorded. Let me check. I hope it's okay. It's being recorded. That's perfect. And the webinar's recording will be later made publicly available. So yeah, you can see it on your leisure if you like. Okay, so let's get into it. I will switch the camera off for a while, and I'll get back later in the Q&A, or let's see. But yeah, see you later, alligator. I'm switching the camera off, and let's start with the webinar details. So there will be still 3 more webinars till the end of the year. So the next webinar will be on November 12th. It will be focused on airfoil acoustic, external aerodynamics, and noise simulation, acoustic simulation, and we will say a little bit about the possibilities of optimization of the noise and noise reduction elements, basically. So it will be next webinar in 2 weeks. There will be another webinar about wind turbines in another 2 weeks, I guess. And still by the end of the year, there will be the webinar 90 about blood pump. So again, There will be a complex workflow dedicated to this, and I believe that in the meantime we will definitely release the new version. So there will be another webinar with the new version, and we will show all the news and new features and everything. Okay, so there are still many things to come. So let's focus on today's webinar. So I will just quickly mention the necessary information which I believe is important. So the company is called CFD Support. It's the company name. We are located in Prague, Czech Republic, Europe, and we deal with CFD simulations. We were based as a CFD consultancy company, and later we extended our services with FEA, FSI, optimization, acoustics, and software, which is our main flagship product. I would say 60 or 70% of our revenue comes from TCAE, which is a comprehensive simulation environment where you can do your simulations. It's extremely useful, extremely flexible, and I would like let me say a little bit about it. So TCAE consists of modules. So there are modules for meshing, there are modules for CFD simulation, for FEA simulation, for acoustics. There are modules for optimization, and few new modules are in the development and will come soon. So it consists of modules. You can use all of them or just one of them. It's definitely up to you. It's up to the users. TCAE is extremely flexible. So you can play such a puzzle with it. You can combine the modules with existing CFD, with existing meshing, with existing post-processing. You can combine them with open source workflow. You can combine them with in-houses. You can combine it with existing commercial codes. TCAE is always here to help, and it's extremely flexible. It's unlimited. That means there are no limitations on number of users, jobs, cores, hardware installations. So you can be sure that you can use your resources to the fullest. There's a wide range of licensing options and collaboration options. So anybody can get this work. So feel free to talk with us about it. And I'm sure that we will always find a solution for everyone. Okay, TCAE is accurate, and because it's focused, that means it's not software for everything. It's specifically focused on turbo machinery applications, and it's focused on external aerodynamics simulations and many other stuff. But these two are, I would say, primer, and they definitely work best. It's not a general purpose code. We're obsessed with accuracy, and we believe it's all about the skills, experience, patience, and dedication. And all this has been packed in the TCAE, in this software. TCAE is perfectly automated, so you can use it as a black box if you like, or you can use it as a fully sophisticated, high-end software where all the options are open. The decision is always up to you and up to the user how it's going to be used. It's infinitely, I would say, flexible in these terms. We have delivered over the time many benchmarks. Some of them are publicly presentable, so we can publicly present a lot of benchmarks where we show how we meet the goals, how we meet the measurements, how we beat commercial software, how we compare to other solutions. So it's really really valuable. It's been tested very extensively over the years, and it really has been proven many times. TCAE has special ability. It has a unique ability to be used in a client server mode. So you can set up the simulation on your computer, but the simulation can be run remotely on the remote computer. It can be used on every hardware. It can be used on laptops, desktops, clusters, PCs, clouds. It can be used from home or from work, of course. It can be used in Linux. It can be used in Windows. It can be used in graphical mode. It can be used in the batch mode. So the workflow is same on all the simulation environments, I would say, operating systems. and also in this using terms, it's very flexible. I guess the last very important point is that TCAE is based on open source. That means that there are a lot of open source codes integrated in TCAE. In fact, there is more than 60 of open source codes. And this is what we acquired over the time. We have mastered the process that how to use the open source, which is freely available out there, and make it usable for the users in the industry with very high added value. And this is really important. Imagine how much effort has been spent over the years on OpenFOAM, ParaView, Calculix, NetGen, all the libraries which are available, and we know how to use them, pack them together, make them communicate, make them connect each other to make a software out of it. It's huge. It's really huge. So on top of existing open source software, we have spent here at CFD Support aggregated 50 plus many years in the coordinated development of really focused team of developers to deliver TCAE. So for these reasons, TCAE is huge. It delivers a huge value to its users, and we believe it's a really great deal to use it. Yeah, there are always new releases. We are developing all the time. Every day we have new versions, in fact. So the very soon we will release the version 24.10. Now it's stable version. It's called 24. It's version 24.3, but 24.10 will be released any day or any week. We have it already, but we are proceeding with final tests, and it's on very good way, and we will release it very soon. For the future, we will keep emphasis, we will keep accent on the optimization module. We believe optimization is the future. Almost everything can be automated, so we believe optimization will be a really big deal. So we will develop the opt for the future. We will keep developing acoustics module. It's really high end and a really big thing, and not everyone can do that. So TCAA is great high-end module, so we will keep developing the acoustics, that's for sure. We are developing a new module which is called T-Base, and it allows the users to create their surrogate models based on their previous results. So it's and big libraries and databases, so it's a really big thing. We believe it's the future, and we are developing it as well, and release it hopefully early next year. And also we are releasing a new light version of TCAE. It's called TCAE Lite, and it will be again huge because it will allow to use this unique technology to everyone, literally to everyone. Everyone who wants to use it will be able to use it. We will come with the details soon. So yeah, there will be the light version, which will be further developed as a GUI for OpenFOAM. So it will go its own way, but still developed under one big development environment called TCAE. But it will be developed as a graphical user interface for OpenFOAM. So feel free to come with the ideas, what applications, what use cases you would like to see in it, and we will be adding new features, and it will become a proper, fair graphical interface for OpenFOAM. That's a very important message. Okay, so that's the details about what we do, and now finally we will go for the case. I'm looking forward to it. So let's start with the topic of today's webinar, which is the Francis turbine. This is our very favorite case. Generally, hydro turbines are very favorite field of turbomachinery and of CFD. We support it very much from the beginning and for a long time, and we believe it's a great field because in good hands you can obtain in standard cases you can obtain nearly perfect results with CFD. It really works. It really fits. This case of the Francis turbine, which we present here, it's important that it's well known. We have the model, I mean the virtual model. We have the measurements. We know the story. It's a real existing machine, and it's been measured, it's been tested, and we can see the comparisons. It's really great test case, one of our favorite benchmarks. So important message is that on our website, let me take a look. I'll go to our website. In case studies, you can take a look on the Francis turbine CFD FEA FSI simulation benchmark, where you can see all the details. What's the story behind it? You can see it's, by the way, it's a really existing turbine in Brazil. You can really read a lot of details. So if you forgive me, I will not mention all the technical details here in this webinar, because you can read it in your leisure time if you like, if you're interested in it. So all the information, or I would say all the important information, is available online. There's PDF report, there's the simulation report, where you can see all the performance, all the times, simulation times, and all the technical results. It can be downloaded, and also the FEA simulation results are there. You can download them too, and see really all the details from there. Yeah, the PDF is also available, and also the case and the geometry is downloadable, and you can use it and test it and to really make sure that everything is there, it works and makes sense. And that's, for us, it's transparent, and for us at CFD support, it's really important to be transparent and to be such a clear and in this message what we do and what we support. Okay, let me start with a couple of general information which I like to tell, because there's never, I think it's never enough of it. So first of all, CFD, computational fluid dynamics, is a special field, and I always say it's not a calculator. Here I mean that in the calculator you put the exact data, and you pull out the exact answers, right? The exact inputs and the exact outputs, and they're either correct or wrong, typically correct, right? Because it's calculator, it never makes mistakes. So, but CFD is not a calculator. There are no exact data, and there are no exact results, right? What you have with CFD is always a kind of approximation of the results. That means that you have something, sometimes good results, sometimes a little bit better results, sometimes you have worse results, depending on your effort, sometimes on your on luck, simply luck, and sometimes it's nobody knows what, but it's always an approximation. We did not invent that. It's a fact. It's the game we play, and we only follow the rules. CFD is always just an approximation. Hopefully we are clear here, and let's go a little bit more in details. But CFD is not a calculator at all. Interestingly, I would say there are still things we know, right? That there are still things we know and we can say. We know what's the uncertainty and where it comes from, and it definitely comes from our effort, right? If we spend more effort, we are more likely will have accurate results, and if we spend for some reason, and it can be fair, if we spend less effort, we can have less accurate results. Let me explain this plot, which I love. It's my favorite, because it says how the accuracy stands against the effort, right? So if you imagine that with the accuracy, here we mean that's the difference from, for example, from the ideal perfect world results, or sometimes we compare if we are not living in an ideal in perfect world, so we are comparing typically the physical measurements. So let's say, okay, accuracy is the difference of our CFD results from the physical measurements. Okay, and if I say, okay, if the difference is 0, we are always there, but as we are there, but as I mentioned, we are never there, because it's almost impossible to meet exactly the perfect results or the measurement. But you can get closer and closer to it, and how much close you get to it depends how much effort you spend, how many resources you spend on your project, on your simulation. That's really important. So we have this effort axis, and here we say, okay, you in every project you make specific decisions, and you have to resolve them to particular levels. So let's say you make successful decisions, right? So you have, let's say, you pick the correct physical model, you pick the correct boundary conditions, you pick the correct turbulence model, for example. So then you make certain decisions, and more decisions you set correctly, the more likely you are getting closer with your accuracy. So for example, you can go easy, say you can decide just quick five specific decisions, like for example boundary conditions, the mesh roughness, and basic physical model, and you already have results which are 50% away from your perfect solution. Or you can go farther, decide, let's say 15 decisions properly, and you're 5% away from your selected from your perfect solution. Or you can go make, for example, 30 or 40 decisions. Okay, it's just a scale, general scale, of course, and you can make almost 30-40 decisions correctly, and then you can get close to 1%, for example, with the measurement. So it's always about the effort. If you're fine with 20%, then you can run pretty much anything and you'll be there. But if you need to go like under 2% with the difference to the measurement, you have to make something like, okay, it's general guess, but anyway, you have to make like 30% of successful decisions in your simulation. That's the message. So it always depends where you are aiming and how much effort you spend. It's a classical trade-off between work and added value and profit. So I hope this is clear, and I think we can start with the case. So at the beginning, I would always recommend to start with goals, because before you start any project, I recommend start with goals. What are your goals? Why are you going to simulate this project, this machine, and why are we doing this? And how do we learn we are there? How do we learn we are at the end? We met our goals. That's very important, because you have to have goals to know where you are. Or in other words, if you have no goals, you will never go. If you do not know where you are going, you will never get there, right? So it's really important to have goals, and preferably to have them right in the beginning. Of course, you can change the goals along the way. That's normal. You can always change the goals along the way, but at the beginning, you have to have goals. Why are you doing this? You should consider what's the project nature, for example. If the project is disposable, if you do it only one time in the history and never do it again, or if it's a long-term process, if you are creating a workflow, right? It's really important decision to, if you're doing disposable project, just have a look at it, look at the results, and run away and doing something else. It's definitely completely different project than than running, than creating a workflow which is going to be improved over the years and the same again. What are your expectations? Expectations are extremely important. They are closely related to the goals. How do I learn? I am there and I finished it. What's my expected accuracy and what's my expected effort to achieve it? Extremely important thing. And another point, for example, will this project will be ever repeated? Will it be shared with other people? Is there anyone who comes after me who will run it after me? Am I doing it for other people? Am I doing it just for myself? Those are extremely important points, and you should always ask them, right? You should always ask them. I can make up some example. For example, so now I hope you can see it. Now I am in the graphical interface of TCAE. So I have the Francis model turbine here, and my goal here could be, for example, there could be a lot of goals, but in this case, I could be following, for example, the complex comprehensive simulation. Of course, it depends how at what stage of your design process you are at the moment. But okay, I would go for a comprehensive simulation, so multiple points, and I want to, for example, explore this. The characteristics of this Francis turbine. So this could be my goal, and I will simulate one speed line with certain simulation points, and see what's the performance of this. So I'll take it easy, but in your case, you should be always sure what are your goals and how to meet them, at least a little bit. So I'll go back to my presentation. It will become clearer and clearer, hopefully. So what's always very important is the input data. The input data is extremely important because it defines your aspiration on the accuracy. So, for example, my colleague Radek says garbage in, garbage out. It means if you put bad data in a CFD model, you cannot expect perfect match with the measurements. I guess this is clear. So the input data is everything. So always take care, a lot of care about your input data, where they come from, if they're accurate, if they're physically accurate, if they're properly scaled, if they're properly cleaned, and if they're ready for the simulation. That's very important. So in the inputs in the beginning of every simulation, your goal is creating the volume mesh, right? Volume mesh is where finite volumes are simulated. The solver uses finite volumes on a volume mesh. Volume mesh is 3D mesh of your machine. In TCAE, you can either import the external volume mesh in MSH, CGNS, or in OpenFOAM format. But you can load it, load finished mesh. But 90% of users they create the mesh in TCAE, so you can use automated or semi-automated workflow to create the mesh. So I will talk a little bit about the data for creating the mesh. So the input data should be created in some CAD system. We use, for example, Salome. It's another open source, and the data can be created, I would say, very well. So we recommend a free software called Salome, or any other CAD system can be used for geometry creation. It's very important to let's say split your model into components. So now I'm getting to this Francis turbine we are going to talk about in today's webinar. So let me comment a little bit. A typical turbo machinery case, which is this Francis turbine, it consists, or we recommend it at least, and we recommend it should consist of components. We call them components. Let me comment a little bit. These components are parts which help us to separate the rotating parts from the static parts. So this is geometry, which consists for this particular Francis turbine. It consists, I would say, at least from 3 parts. It can be many of them. It can be 10 parts, but okay, for simplicity, we pick 3 parts, and it will be spiral. That means, the spiral part, this large volute part where the water comes in, and every component should also have the input. So it's the interface where the flow or the water flows in, and the output where the water flows out. So now here it's called inflow, and the interface guide rod. It means it's the interface where the fluid or water leaves the spiral and enters the rotor part, the impeller part, the runner part, for the turbines. So it's the inlet, outlet, and then solid walls, typically solid walls. It could be the spiral itself. It could be little tiny details, the spiral dip, this tank, and it could be shroud, hub, and also blades of the guide blades, I mean, and also guide hub and guide shroud. So these parts it's just an example how the component spiral can be split, and another part could be the runner. Runner is again it's rotating, and it's important because it's rotating. That's why we are splitting the model into 3 parts. So again, there's the spiral, there's the runner, and there is the draft tube. So these components, and I'll get back to the runner. So we have this runner part which can rotate, and we can prescribe the special boundary conditions that allow us to use to have the rotation in it. So it can consist from for example, from the blades, from the hub parts, and it can consist of the interface. That it must consist of the interface to the draft tube, interface to the spiral, and also static parts and the rigid wall parts. So I have 3 parts, 3 components here. Again, spiral, the runner, and the last component is relatively simple. It's large one, but simple one, and that's the draft tube. So my draft tube is basically a large channel with the inlet part, with the outlet part, and with a wall part. So I have these 3 parts, and all of them, we have a couple of requirements on them. They have to be waterproof. Each component should be waterproof. The components are connected via interfaces. So again, the interface from the spiral is called interface guide rotor, and it's the inlet interface for the next next part. And again, the outlet of the runner is the inlet for the draft tube. So components, watertight components, each of them has the inlet, the outlet, and the walls. Everything is absolutely flexible. You can create your own model, but this model is just this, I would say. So the input data, the model is split into the components, and we inserted them to TCAE as individual STL surfaces. So I could I could show it here that I create, for example, in the Salome case, I can create these individual STL files, which I insert in TCAE. It's relatively simple. You load them, you load the directory, or you import them to be coded in the case. There are options in this, so I can pick. Yeah, I will pick just a few. Let's take the spiral to be clear, and I'll also take draft tube and blades. That could be transparent enough to show what we are doing here. And so these individual surfaces are loaded in TCAE, and okay, it takes some time. They're relatively fine, and so I've loaded a few of them, and here you can process them. So you create the individual surfaces all the time. Okay. So yeah, the surfaces they have to be watertight. They have to have interfaces to connect with other surfaces, with other components, and they have to have walls. This part is relatively important. It's in fact it's really important because we call it cleaning, scaling, sealing, and sorting into the simulation model. So your model has to be clean, waterproof. Like sometimes we say it's sealed up, like yeah, to be waterproof and cleaned enough. And sometimes we say it's a quote from Albert Einstein that your model has to be simple as possible, but not simpler. So keep it as simple as possible, but not simpler to make it too simple. But anyway, keep it simple, make it clean, scale it to the real dimensions. It's really important. Many people forget to scale it, and then they are really disappointed with the result because it should be scaled, and we recommend to have the model scaled completely physically, not to scale it numerically. It's possible to scale it numerically, but we recommend to avoid it because it decreases the chance to make any stupid mistake with units, etc. So keep it scaled, keep it sealed, and sort it into yeah, this cascade of components. In TCAE, you can also look if you did everything right. We have a special feature we called component map, and you can see that we have 3 components here, names of the interfaces, what interface connects what interface, what component connects what component, and here is the cascade where the flows enters the spiral at the interface called inflow, and leaves the whole machine at the draft tube interface called outflow. So the connection is made this way. It's not a big deal. I can talk about it a little bit later when we talk about the mesh, exactly the mesh. But this cleaning part is the bottleneck, and you should deal with it to a particular level. Otherwise, there could be expected issues. Anyway, I hope it's not looking complicated. It's not complicated at all. It's like riding a bike, right? No one is best in riding a bike if you ride it first time, right? If you ride first time a bike, there's a huge chance you won't be the best in the world. But if you do it more times, then it goes easier and easier, and you do not think about what to do, where to turn around, or what to do. So it's like riding a bike. It looks complicated in the beginning, but it's easier later. And another point is almost anything can be automated. So even the pre-processing can be automated. Even the cleaning, scaling, sealing, and sorting the model, everything can be automated using Python or other scripting languages. So don't worry. we can help with it. So anything can be automated. But this is the bottleneck, creating the geometry. While creating the mesh, it has another set of rules that are similar, but if you have good geometry, good starting point, you have very, very good chances to succeed in the rest of the process. When you want to create the mesh, you have to mesh each component separately to merge them in the full mesh. So again, each of these components, each of these three components will be meshed independently. So there will be mesh for spiral, there will be mesh for a runner, and mesh for the draft tube. And if we like, we could run just one component. But of course, we will merge them together to run it in a one big case. But there will be, in fact, there will be three like independent meshes which will be merged together. So three meshes which will be merged in a one complex mesh. So that's the reason why all the components have to be watertight. Really important. They have to be watertight and waterproof, sealed up. Yeah. There are a couple of parameters you have to be sure you set correctly in the beginning, and I will comment on them. So if you have these components and you use the T-Mesh module, you go into the settings, and extremely important part in the CFD mesh is the part components, where you say how the individual components are meshed. So as mentioned before, every component has its own mesh. Component has to be waterproof again, and each of them has its mesh, and the TCAE can join the meshes. It can connect the meshes. That's not a big deal, but you have to mesh them individually. So you load the STL files here. You can either completely import them and they become part of the project, or you can use external folder where you can only replace the STL files and with every new simulation and have new results for every new set of your data. Some kind of settings is useful in different projects. Sometimes it's useful to have the geometry used externally. Sometimes it's useful to use it in the project. It depends what kind of projects are you running and what are your goals. Goals are always important. So in this case, we have imported the individual STL files. For example, for spiral, it's guide, hub guide, guide blade, guide shroud, and inflow, and the interface, and spiral tip. And for a runner, it's similar. For draft tube, it's even much more simpler. And what's important is there are a lot of settings, of course, but there are only a very few settings you should know in the beginning, and you should know what's your basic background mesh size. It's really important. It says what's the biggest mesh cell in your simulation. It can be either cube or it can be a hexahedral. We recommend cubes for standard projects, and you say it's 12 centimeters. So yeah, it's huge. I mean, the spiral is huge. So 12 centimeters is the basic cell, which gets refined. So the biggest cell is a cube with the edge of 12 centimeters. That's really important. And so background mesh size, absolutely critical parameter. And then you also should prescribe the internal point. It says what's the inside and what's the outside of the mesh, because the solver does not know, the TCAE does not know without your help. So tell me what's the internal point. So you specify the point inside the mesh or inside the flow, the point which in water, basically water point. So the internal point is important to be specified. You can visualize it. No, let me say this is the dot. Yes. So yeah, you have to say what's your point. You say what's your important point, and you do the same decisions for all components. And another important is refinement level. You have to say how many times is the background mesh being splitted towards to the surface. So At important surfaces, you refine quite a lot. At not important surfaces or at the interfaces, you don't refine the basic cell at all. So those are refinements. So 3 important meshing points, and I'm fine with this. It's the basic mesh cell, it's the refinement and point inside the mesh. These 3 you have to know, and you will have the mesh, and then you can improve your simulations. What's absolutely super critical at CFD simulations is the mesh size. Sorry, the mesh size. How big is your mesh? It tremendously affects all your future simulation parameters. So small meshes are quick, maybe not that accurate, but you very quickly see the results. And in the beginning, it's very important to see the results as early as possible. So we definitely recommend to start with smaller meshes. We recommend to start with small meshes to make a few quick iterations in the beginning to make sure you did everything well, and then you can always refine the mesh, and you can always go for big simulations with that aspire for I would say accurate results. But I definitely recommend start with small meshes and quick simulations because it allows you to iterate in your process in the beginning. And again, hopefully it does not look that complicated, and if it looks complicated, it's not complicated. It's like riding, remember, it's like riding a bike. If you do it first time, it's difficult, but when you do it second time, third time, fourth time, and if after months or years, you don't even think about it. It's the same with the simulation. It's simulations. It's like riding a bike. And again, there's everywhere in the workflow, there's a huge chance that it will be repeatable. There's a huge chance it could be automated, and there's a huge chance you can only improve your workflow. So what works, you keep it. What does not work, you just change it, right? So you always improve along the way. That's really important to. It's really important to do not get annoyed or disappointed in the beginning, because it's difficult to start, but then it's really beneficial to use using workflow. Regarding the simulation setup, if you have the geometry, have the mesh, the simulation setup is the way easier. Everything is easier then, because of course you have to think a little bit what are your outputs. We recommend to make the setting accordingly to your outputs, right? So if, for example, in case of such a hydro turbine, Francis turbine, it's not a big surprise if I comment that you typically go after the efficiency. Efficiency is, and at turbo machinery, efficiency is everything, right? Because you have to use your energy efficiently. Either the machine consumes the energy, like ventilators, compressors, or pumps, or it creates the energy, right? The hydro turbine, all kinds of turbines, all these machines, they produce the energy, but every time you have to have great efficiency, because you spend your energy efficiently and in a smart way. So it's all about the efficiencies. So to set up everything according to the best efficiency. Evaluate the efficiency all the time during every iteration, during the simulation, and evaluate and look at it, and based on the results, you can decide whether the simulation is finished, etc., etc. So in the beginning of every simulation, you should decide what are your physical times, right? What are your physical times? How many points you want to simulate? If it's just one point, if it's just the best efficiency point, whether it's the point you want to get as close as possible to the measurements, to validate, to make benchmarks. What are your time options? Whether you want to simulate steady state or transient. Again, you can make aspirations to very accurate simulation for of 1 point, perhaps the best efficiency point, or you can be interested in the whole characteristics, whole maps, and their envelopes, and really complex simulations very early in the design process of your machine. So again, it's all about your goals, but in every simulation you have to decide what are your points, how many simulations are you going to simulate, and if you're going to go for steady state or transient. It's a really big, perhaps the biggest decision concerning the TCFD setup. Then you have to, okay, I'll show it. So in TCAE at Francis Turbine, it's in the TCFD module where in physics you have time management, and there you decide whether you go steady state and transient, or just transient. Then you say how many speed lines. It can be just one speed line or more speed lines, and each speed line can have several points, and so you can say how many points. So in this case, because typically Francis Turbine is designed for one fixed RPM, right? It's designed for fixed RPM because of the motor, and everything is fixed for hard shaft and everything. So you know your RPM, you know your revolutions over time. So typically you simulate several speed lines to see the fluid characteristics. So let's get to it a little bit later. So yeah, so the decision is 10 points of the characteristic of this speed line, and a very steady state, and 10 points of one speed line, and a number of iterations. I mean the raw iterations, which the simulation can be stopped when it reached the convergence with the stop criteria. But anyway, it's the steady state 10 points fixed RPM decision. Another decision is the physics. So let me see. Another very important is this. So what's the fluid? What's its what's the fluid's the parameters? So dynamic viscosity, reference density, reference pressure, etc. You should decide the solver. Of course, I say it quickly to show you the most important parts. So you have to decide the solver, which is incompressible, which is incompressible solver, basically with the water parameters, and you have to decide what is rotating or not. You say how fast was the RPM basically of the runner, and we previously in the mesh we said, okay, the runner is rotating, what parts are rotating, and that's we set it in the mesh already. Now we are in the simulation settings. There are a lot of potential settings you can set, but you can leave them empty. There are a lot of good defaults which allows you to run almost any simulation. You decide the solver, how many processors, that's important. So how many physical cores are on your computer. The second order, of course, equations, and you can set up, for example, what's the averaging window, how often we are, what's the window where we carry the averages over the simulation, what are the stop criteria, what we will evaluate. You can evaluate forces on every part of the project, on every part of the mesh. And you can evaluate probes, for example, to compare with the measurements in space in the fluid. And there are a lot of other options. I'm not gonna go too much in detail because the time is running pretty quickly. You should definitely decide the turbulence settings. So if you do not know anything yet, we recommend to use K omega SST with standard default settings. And what's important and really extremely important is boundary conditions. We should comment here. So in the simulation settings with this Francis turbine, we recommend to use, if you do not know anything else, we recommend to use flow rate at the inlet. So we have these 10 points, as I mentioned a while ago. We have volumetric flow rate in cubic meters per second set at the inlet, and at the outlet we have fixed pressure, fixed to 0, which means the basic reference level of the pressure. So boundary conditions are extremely important. For each point we need a set of boundary conditions, and that's pretty much the basics. You should always decide for what are the outputs for the post-processing. That's really important because for turbo machinery you can be interested in, for example, in the blade-to-blade views, the volume fields are written down automatically, but you can be interested in even more, like meridional averages and various report units, and you can use your additional data examples and all that can be included in the report, which is for every simulation is a special report with the results. And so that's the settings here. And when you're fine with the settings, you should run the simulation. So TCAE has the standard project management, so you can save the project, save it as another new project, or create new projects from other project, use the old settings, new settings, play with everything. With every new project, you typically would work in an iterative process. That means you do the settings as you did it all the time, and see if everything works well. Typically it works, everything works well, and you do the simulations. I should mention, yeah, so we did in this preset case, which works. We have run it literally hundreds of times, and we know it perfectly. So the volume fields are written down automatically. The integral fields are written down in the HTML report, so you can take a look at all the simulation details. What are the integral details of the simulation, and all the important statistics. You can look at what's the pressure, what's the characteristic of the head, what's the characteristic, how it developed over the time and over the simulation points. Yeah, here I skipped because when I was preparing this case for this webinar, I skipped the simulation too early because I was worrying about the time, so I skipped this middle point and a few other points too early, but no worries about that. And there are a lot of integral results in the HTML report, which is generated after the simulation is done. You can see various coefficients and various details and angles and pressures, and also, yeah, there are a lot of details where you can see how the velocity was developed over the interfaces, for example, or how it worked. So this case has been explored very much in the detail. There are cavitation there are cavitation functions that are developed, evaluated in the simulation, even for steady state in transient simulation. It can the cavitation can be done properly, really, in the multiphysics and multiphase. In steady state, we have some functions. The blade to blade can be evaluated, as well as meridional averages. So there are a lot of characteristics that are developed for every simulation. Yes, every simulation you follow how it develops over the time. So you can see the residuals. You can see for example, the efficiency, which is our favorite quantity, where you can see how the efficiency developed over the time, and see when it was stopped by the stop criteria. You can apply them on the immediate values, or you can apply it on averages. There is enough flexibility everywhere. So hopefully this is clear too. Volume fields are available, so you can look at everything in detail. And we recommend it, because sometimes integral results could be misleading. So we always recommend to look at everything visually, at volume fields, how they yeah. This is strange a little bit, but anyway, I'm not going to spend that much time here. Anyway, the volume fields are clear, I guess. So you have all the quantities, all the boundaries, and all the volumes and volume fields for every case written down. So you can go after them. And I didn't what I didn't mention, and I should have mentioned it, is it's not only CFD. The CAE has also the FEA module, where you can simulate the model analysis, the material stress, and the deformation. So I'll say that the similar principles what we have seen in the CFD mesh, the similar principles can be followed, or have to be followed in the FEA simulation. So again, the STL is of the solid part. Now it's the runner. So the runner, the runner solid is like the input. So we have such a runner, and DCAE can use Calculix. The Calculix is created, compiled in DCAE, and it can use the FSI forces. Those are fluid forces which are acting on the surface of the impeller, and Calculix can or Calculix-based solver can run the simulation and show the material stresses, and also model analysis, and also the deformation. So it's important part of a complex simulation. And let me take a look back to the presentation. Yes, so it may look complicated, but it's not. As I mentioned before, almost anything can be automated. There's a huge chance that it could be, and if any work you did can be repeated automatically. So everything is just a matter of automation. Yes, so yeah, the simulation is iterative process. That's what I mentioned. We definitely recommend to start with small meshes and slowly increase the number of mesh cells, because you can always make big simulations which are really large and take a lot of resources to simulate. So start with small meshes, follow flow rates, follow residuals, and follow the final quantities. Always do the visual checks. and always, of course, follow the integral values, because in turbo machinery, in turbo machine simulation, in turbo machine simulations, it's all about the integral values. At the end, it's all about the characteristics of the head, for example, or of the characteristics of the efficiency and torques, and etc. etc. Okay. I think this could be it from this presentation, because the time is somehow running faster than I expected. I will continue with this quote or a wisdom that the technology is only 40% of your success. The rest is skills, experience, patience, dedication, and your focus on your case, on your particular project. Every project is different. The devil is always hidden in the detail, and it's all about your effort. How it will be resolved. The software pieces available in the market are somehow, to some level, they're similar, but it's your persistence what makes you successful. That's for sure a biggest, if I would say it's the biggest point I would like to make. And because the time is running, I would like to ask you to ask your questions. Please ask your questions, and I'll do my best to answer them, and do my best to really help if I can. So it's your time, and the stage is somehow yours. So feel free to ask your questions. In the meantime, I'll give you a couple of seconds, because I know it's not easy to raise a hand and really come up with something. So what should I say? What have I missed? The big point is the riding a bike, right? Simulations, they only look, they're complicated, they're complex. In a way, they are complex, but to use them is simpler than you think. It's like riding a bike. That's really the big point. So anybody can get there. You do not need any special talent. You do not need any special resources. You do not need any special hardware. You need only the willingness to deal with simulations, and your persistence and willingness to overcome the child diseases of your early workflows. So that's definitely the point. And listen, I'll be honest with you, I can't see any questions. I don't see any questions. People are here, but no one asks anything. So the time is running, so I'll give it another couple of seconds, and then we will close and conclude, I would say, the webinar. So well, I can't see any questions. Yeah, this is not happening very often, so but there are no questions, but okay, that's the deal. So did I? Yes, I'm there. Hello. Yeah. Yes, I'm here. So yeah, this could be it. Today we don't have any questions, but don't worry about that. Feel free to come back later. We will do our best to answer everything and make everything clear, make everything transparent, and let it up to you whether you think it's worth to deal with or not. It's really always up to you. We do not push too much pressure. Simulations are typically a long-term run. You very rarely make anything quickly successful. So yeah, this could be it for today. I would like to thank you for your attention. I would like to thank you to spend some time with us. Keep following. We have always a big news, always new developments and new things to come. So yeah, keep following, and this could be it. I leave you with that for today, and bye bye. Thank you everyone. Thank you for joining. Thank you for listening.